Welcome everybody to the online seminar series, Machine Learning Needs Mathematical Optimization. We have the pleasure of having today Gah-Yi Ban, who is an Associate Professor of Analytics and Operations at the Imperial College Business School and an Amazon visiting academic. Prior to joining Imperial College, Gah-Yi was a faculty at the Robert Smith Business School, University of Maryland, and at the London Business School, and was a visiting faculty at Columbia Business School. She obtained her PhD from the University of California, Berkeley, in Industrial Engineering and Operations Research. So her research is around big data analytics, and her work has appeared in leading journals in the field such as Operations Research and Management Science. She has also been honored with the 2021 Best Operations Management Paper in Operations Research Award, and as well as other prizes. She's currently an associate editor of Management Science, EMSON, and Operations Research Letter, and a member of the World Economic Forum Expert Network. And I have to also add that she has given a TED Talk. So I think we have a great researcher and a great communicator today with us, and we are very pleased that you said yes to our online seminar series. So the floor is yours, and for the audience, we follow the usual rules. If you have a very urgent question, put it in the chat, and if not, you can ask at the very end of the presentation. So the floor is yours. Thank you so much again.
Okay, well, thank you very much for the kind introduction. So now I have very high expectations to me, but this is the first time I'm presenting this particular research. So, I hope your expectations aren't too high. So this is based on ongoing work. We're close to submitting the paper. And this is joint work with colleagues Hichame Benbitour. He's an assistant professor in Normandie, and Boxiao Chen. She's an associate professor at UIC Business School. So this is about selling personalized upgraded substitutes and co-purchases in online grocery retail. So how did we get onto this particular topic? Well, I mean, there's been in the community a lot of interest in online e-commerce, especially in the revenue management community. And get so online shopping, I mean, this is a massive trend. So if you just look at the US alone, going from 2010, just 6% of total sales in any goods used to be online, and this rose to 16% in 2019. And during the pandemic, all this online shopping has really accelerated during the pandemic, and so online shopping accounted for 27% of all sales across categories by April 2020. So now, I attended the Harvard COER workshop, where you get to meet some industry practitioners as well as hear from academics, so I got in touch with some practitioners so I cannot name the company name, but I'll just say it is a leading grocery retailer in the US. And so I started this conversation with the industry practitioners and realized that so now, while I had thought that online grocery shopping was something prevalent, but actually realized this was actually really a recent phenomenon. So, so before non-perishable goods were really the reserve for online shopping, but the pandemic has accelerated people's behavior into shopping even for groceries online as well. And so this is continuing, but of course, just like working habits, we're kind of in a hybrid world right now. However, what we're seeing is that so during the pandemic, some people may have shopped from places like Ocado, which is like an online-only retailer, or you have big physical store giants realizing they need to go online as well. So those are companies like Sainsbury's and Kroger in the US. And so, so this was an interesting question for us in terms of so what are like the new the unique challenges presented to online grocery retailers in particular. And I'll just mention this is of course like multi-billion-dollar industry which is always growing all the time. And of course there are unique challenges here. So so compared to other product categories, grocery products are refreshed a lot more often. So there would be, say, new types of brands or new products within the same brand introduced all the time. Fresh goods, you know, there are seasonalities, so some things come in and out. And also, customers are much more price sensitive to groceries and also fickle. So, I mean, how many people only shop from just one particular brand? You know, that's really unheard of, right? So, uh, so yeah, so there are unique challenges for grocery retailers. However, there are also unique opportunities, especially if what's, you know, traditional physical stores want to go online. Suddenly they will be able to really gather customer data and customer click-through behaviors in real time. And so they should be able to make real-time recommendations as the customer shops. And so that is essentially the focus of our research today. Whereas, of course, before, if you only have people shopping for groceries in the store itself, there's, yeah, so you can't do too much in real time. So what we discovered through many conversations with our industry partners is that so unlike what people think a lot, or you know, a lot of the academic work done in revenue management, revenue is important, yeah, but these companies, you know, they've been around for many years, and they understand that short-term revenue maximization is not necessarily going to be a good idea for the long-term long-term survivability of a company. And so they care not just about revenue, but really just as much, or perhaps even more, about retaining a loyal customer base and also growing that over time. And so that is something we discovered through our many conversations. Okay, so so what are our research objectives here? Well, we wanted to understand how could an online grocery retailer optimize for revenue and customer retention slash growth. And the particular lever that we had, of course, there are many ways that you can, you know, try to achieve this objective, but the particular level we had was that so the company we were speaking to, they really wanted to improve their recommendation algorithm. So in particular, you know, what's particular about grocery shopping is that typically people don't buy just one thing. You have a basket of goods to add to your shopping basket. And so, so there is that opportunity after each click to be able to make a recommendation. And so that was the lever we wanted to, or we were exploring to optimize. And so what we're proposing here is to make personalized recommendations, and not just for substitutes, but upgraded substitutes, and also for co-purchases. So that's what we're going to do, or that is what we're proposing. And so that would be online. You can make that happen as the customer puts items into their basket. And in terms of the optimization model, we consider several different objectives. So we consider expected revenue maximization. And so these are actually quite new to the literature. So revenue maximization, of course, that's been done before, and that's, you know, the most of what revenue management literature is about. However, we wanted to consider, say, consumer surplus maximization as well. So that's the second objective we consider. We also consider, say, a weighted average of expected revenue and consumer surplus, right? And finally, the final one is an idea we got after speaking to the practitioners, which is that the size of the shopping basket matters. So there was this fairly empirically well backed up hypothesis that so if a customer tends to buy many different items, so in other words, are able to satisfy a lot of their grocery needs for the week or for the coming week from one particular shop, then they tend to be loyal to that shop. And so for that reason, we also looked at maximizing the expected revenue subject to an expected variety constraint, where by variety, we're measuring the total number of different items in the basket. Okay. Okay, so here is an example of what could happen. So say a customer picks this one particular product, and then what we want to do is optimize the recommendation of potential substitutes, as well as the potential co-purchases together with this water bottle. So yeah. So right now, this particular company is doing something, I suppose, but we're hoping to be able to do better than what's known out there. Okay, so where is the current literature in this topic? So our work, it relates to three broad categories of existing academic literature. The first is on substitution effects in revenue management. So yeah, there's been a fair number of papers on this topic, and also going extended to more recent years as well. And also we're touching on the effect of co-purchases in revenue management. And I must add here that interestingly, there are many more works on substitution effects than co-purchases. So yeah, so we thought that this was interesting. And also our works, because what we want to do is be able to make personalized recommendations. It touches on personalization in revenue management as well, which has in recent years really grown in interest. Okay, and so how does our particular work, how does it extend these areas? Well, first of all, we are considering non-revenue maximization objectives as well. So as I mentioned, we're looking at consumer surplus. We're also looking at things like variety constraint. So the only other paper that I'm aware of that looks at objectives other than pure expected revenue maximization is this one here, Sumida et al. Other than that, we don't know of any to the best of our knowledge. And what is also unique about our paper is we consider both substitutes and co-purchases. So what we found in the literature is that people consider either or, but not really together. And finally, something else that matters perhaps in a technical sense is that what we're doing is making a recommendation, like a conditional recommendation, in that because we're making recommendations as the customer shops through their shopping journey, our recommendation comes after observing the initial choice. So this means what we're going to propose is like what's known as like what we call the conditional utility model. And so this is a bit different from what people have done in the past, which is not conditioning on a particular initial choice. Okay, so yeah, so those are some broad novelties in our paper. Okay, so let me introduce some notations, and I'll walk you through our model and our algorithms and so on. So, okay, so what we consider are the following. So the retailer has a universe of end products, and these products have they have features associated with them to describe what they are. So we call that XP. I is for the particular product I. And we also have customers, And we allow for personalization. And to allow for that, we say the customers, each customer J is associated with a particular feature vector XC. Okay, so that can be lots of things like how many people are in your household, your gender, your age range, your income level, and so on and so forth. Okay, and so this is the sequence of events we assume it happens on this at this retailer. So um, so before entering the website, we assume the customer has a shopping list already, and so there are little n number of different items on their shopping list, and they select items from their shopping list one by one. And once they select an item, say I tau, so tau is the index for the item from the shopping list. So I tau is the tau product from the initial shopping list. And so once they select that item and put it into the basket, we assume the retailer can make at most K substitute recommendations and at most K co-purchase recommendations that pertains to this particular product I tell. And so the customer then makes the decision. They will first observe the upgraded substitutes, and they will decide whether or not to substitute with that recommendation. And then once they decide that, whether or not they do it, they then get the co-purchase recommendations, and then they'll decide whether or not to add a co-purchase to their shopping basket. And then that finishes that particular step of the shopping experience, and afterwards they will continue on to the next item from the shopping list. Okay, and so they'll continue down the shopping list. Okay, some more notations here. So if there's a customer J is shopping at period T, then we have that step. So we have n steps, small n steps. So that's the size of the initial shopping list. And so we have product I going from N1 to T. Sorry, T should be the customer number. And then we do allow for more than one purchase of an item. Okay, and so that's the Q. Q is the purchase quantity. And then they get a set of recommended substitutes, so the S's. These are the recommended substitute sets. And then we have the quantity. The customer chooses whether or not to substitute and whether or not to purchase more than one item. Okay, and then there's the customer choice, whatever they choose. And then they get the co-purchase recommendations, the set C's. And the customer can of course, choose nothing, or they can choose more than one or more of the recommended co-purchase items, and so that will be their customer's choice. And then, of course, the whole shopping basket is then updated accordingly. Okay, so now we model the behavior of the customer to be utility maximizing. And I'll show you the personalized utility model in a few minutes. So now, for each customer and for each product I, we assume there is a consideration set of potential substitutes and a consideration set of potential co-purchases R. So curly Q and curly R. And now we do make this assumption, which is that the retailer will make recommendations from a universe of products that's not that is unknown to the customer. So this could be because there are many excuse me, there are many new products being introduced all the time to the shelf, or new brands being introduced and so on, or just items the customer may have never considered in their past shopping history. Okay. Sorry, I have a bit of a cough, so. Okay, yeah, so that's, we do assume that. And so what that allows us to do is that any recommended items were not already considered by the customer, and and consciously taken off their initial shopping list. Okay, so that whenever the customer gets the recommendations, it's of products that they've just not seen before, and so therefore that is why it's not in their initial shopping list. So this is an important assumption. And then when a customer picks a product, the retailer chooses a subset from this universe of unseen products to that particular customer. And so the retailer will choose a set of recommended substitutes, curly S, and a set of recommended co-purchases, curly C, from these consideration sets. And if a customer, there are a few more things I would just like to mention. So if a customer chooses a co-purchase, we will here assume that they only pick one item from the recommendation, the list. Of course, this can be generalized, but just for the sake of illustration, we thought we'll just stick to one co-purchase item, but it could be multiple quantities. And then something I wanted to emphasize here is that we're considering co-purchases, which, by the way, is an umbrella, is like a superset of what's known as complements in the literature. So complements has a much more technical and precise definition, which is that if the price is increasing or decreasing, so if the price changes in one direction, then the demand for that item goes down or up. Respectively. So complements has a particular technical definition, but by co-purchase, it is more general than complements, and we're just looking at the probability of an item being purchased together with the initial choice I being non-zero. Okay, so this is a slightly, it is a superset of what's known as complements in the literature. Okay. Okay, so in order to come up with an optimization model, we first need to specify a utility model. And so what we have here is a conditional personalized utility model, and condition because it's conditioned on the particular initial choice of the customer, so which I label ITAL, and UTI, so my customer is T, and so here I have the utility of customer T for a new product I, given they have already selected product I tau. And we model that. We have a linear model for the deterministic part. So we assume that this personalized utility model is linear in the customer features, the product features, and then we also have a binary indicator here for whether or not the new product, the recommended product I, is a co-purchase of the initial product I tau or not. Okay, and so this is a binary indicator here. And of course, we need to figure out these coefficients, beta 0, beta, gamma, and H with a data set later. We have to do that. We have an error term. And to allow for a choice model, multinomial logic choice model, we assume that this error term follows a type 1 extreme value distribution. Okay, so this is our personalized utility model. Personalized because we are using the customer features. And then, yeah, so we do need the product features as well, because obviously so here we're talking about the utility for a new product I, and so the features of that new product I, which is XPI here, so that is going to affect the utility for that item. Okay, so now of course, and then here this binary indicator term. So if we're looking at substitutes, this V is just 0. Okay. All right, so now based on that utility model, then we can start writing down expressions like expected revenue and so on. So the expected revenue, we can write it down as follows. So that is quantity, Q tau times PIT. So that's the price of the initial choice and the quantity for the initial choice. So that's just the revenue from the initial choice of the customer. Now, so this is expected revenue after the customer's decision to substitute or not. So if a customer So of course, we are going to optimize over the substitute set S later. But so for each item in that substitution set, if a customer does substitute, then the initial revenue from the initial revenue from that initial choice is not going to matter anymore. So we need to subtract that. Instead, we have to add on the revenue from the particular substitute that was chosen. And of course, that depends on whether or not that substitute was chosen, which is given by this indicator here. So EIS is the indicator for customer choosing to substitute their initial choice by product I. And Q here, capital Q here, is the random variable for the fact that they've chosen quantity Q of these items. So this is the expected revenue contribution from substitutes. And then now let's look at the co-purchases. Well, from co-purchases, you're only adding items, so you're going to just add the expected revenue of buying any co-purchases. And EC here is the binary indicator for whether or not the customer chose co-purchase product I or not. Okay, so that's expected revenue. So now let's look at the expected consumer surplus. So what is consumer surplus here? So consumer surplus is the utility minus the price paid for the items. And so yeah, so the expected consumer surplus for the initial choice. Okay, so that's the first term here. But of course, now we need to add and subtract. If the customer chooses a particular substitute I, then we have to subtract the initial choice, because a consumer surplus of the initial choice, but add on the consumer surplus coming from the substituted product. And then, of course, here we're looking at the expected consumer surplus from the co-purchases, any co-purchases. Okay, so this is expected consumer surplus. And finally, let's look at the expected variety. So we denote by V. So expected variety. So when you think about it, so from substitution, if a customer substitutes, then the variety from the initial choice, well, you always have one, right? So you have the initial choice, which is one product. You substitute that with another product. That's not going to affect the variety. So yeah, so you have a one from that substitution part. But if the customer adds any items from the co-purchase recommendation set, then you are going to add to the expected variety. And so from the co-purchases, you are going to get additional terms. Okay, so now let me write down the full optimization problem. So here we're trying to maximize over all possible recommendation sets of size K or for substitutes and co-purchases from the respective consideration sets. And here what we have, so this is the problem in the full generality. So here I have that, yeah, so here I'm looking at a weighted average of expected revenue and expected consumer surplus maximization subject to expected variety exceeding some parameter nu. So lambda is my parameter for the weighting in the objective function, and nu is the parameter for my constraint. And so this problem I'm going to call RCSV. So R for revenue, CS for consumer surplus, V for variety. And this is parameterized by lambda and nu. And so RCSV 10 would be, well, if nu is 0, then you don't have any constraint there, because yeah, variety is always going to be at least 1. And lambda equal to 1 means you don't have consumer surplus. So RCSV 10 is just the traditional expected revenue maximization problem. RCSV 1 nu would be expected revenue maximization with some variety constraint. And RCSV 00 would be a pure consumer surplus maximization. Okay. And then I would like to note for the general problem, the problem it does decouple for substitutes and co-purchases. And main reason being because of what I've shown you about the variety constraint here, because substitution, it doesn't matter what substitution set you recommend, substitution always gives you just one constant as in the variety constraint. Okay, so the two problems decouple, and so we can consider solving them separately. Okay, so so of course, in general, so I mean, we are talking about finding optimal subsets of larger sets. So this is a combinatorial problem. However, we are able to show that for all the cases that we want to consider, you are able to solve these problems in polynomial time. And so, so I can summarize the results or the computational results here as follows, and I'll describe them more in detail afterwards. So, so as I mentioned before, the full problem, it decomposes into substitutes and co-purchases. We could look at pure revenue maximization. For substitutes, you can solve this by a bisection search algorithm or a sorting algorithm. For co-purchases, you can use the sorting algorithm. For consumer surplus maximization, you can use sorting algorithms. For revenue and consumer surplus, so the weighted average of revenue and consumer surplus maximization, you can look at, so for the substitute problem, so this was actually solved by a related paper, Sumida et al., 2021. And for co-purchases, for revenue and consumer surplus weighted average maximization, you can solve it also by a sorting algorithm. And now, actually, let me just mention here that this revenue, the weighted average of revenue and consumer surplus, so that is something we thought would be important for the company to maintain the customer base and also to grow their customer base as well. So we thought this would be a good way for them to balance revenue and growth and just the customer retention and growth. However, our industry partner also mentioned that things like the variety of shopping or the amount of goods that their one retailer can satisfy the customer's grocery needs is really important. And they found in their internal research that this really helps with customer stickiness or retention in the customer base. So so this third problem is something we came up with as academics, and this final one, which is expected revenue maximization, but with the variety constraint. So that is actually something our industry partner suggested we look at. Okay, and so so that came about these two types, and then so for the substitute case for expected revenue maximization with variety constraint, because of the decoupling, you can use the same bisection search algorithm or the sorting algorithm from the pure revenue maximization problem. But for the co-purchases, you can't just do the sorting algorithm from before. You do need to use what we call augmented Lagrangian method. Okay, so let me go into a bit of details. Okay, so just looking at the time, I don't want to bore you with too many technical details, but I just wanted to give you a flavor of the kind of results needed. So computing, let's look at the optimal solutions for RCSV 10. So that's the pure revenue maximization problem. And for here, I've already alluded to that you can solve this by a bisection search or a sorting algorithm. And to get to that stage, so this was actually perhaps the most difficult problem to solve. We had to go through several lemmas. So to find the optimal substitution set, we can show that's equivalent to maximizing this set function here, M. And then we show that, first of all, we have to show that the expected revenue of the optimized substitution set is equal to for some theta, so there exists some theta such that the revenue function of this m function here evaluated at some theta is equivalent to the optimized revenue. And then we had to also show that this theta, so not only exists, but is also unique. And then, so we had to go through a few more lemmas and introduce a new function g here. So there exists a unique theta such that blah, blah, blah. In other words, you can find a unique theta that satisfies this equivalence here. And then we have a few more lemmas to show that essentially, yes, theta exists and it is possible to find it. Okay, so now, yeah, so here we have these f functions here, and this is just to illustrate roughly how this algorithm, the bisection search algorithm would work. So essentially we have this equivalent problem and we need to be able to solve for the optimal theta, which is unique, and it exists and is unique. And we show that the whole problem translates to finding, say, the largest. So for each value of theta, so on the x-axis here, I have theta. And for any value of theta, I need to be able to rank these functions f's. So these are these functions here. And then once you are able to actually once you're able to rank them, so say for theta 1, so if the optimal theta was theta 1 and you were only allowed to recommend 2 items, so on the screen you can only fit 2 items on the screen, then essentially the optimal solution is to pick items, this one, this is for product 1, and this one, this is for product 2. And this, of course, if we could recommend 4 items, then we can recommend all 4. And just mentioned, yeah, so any items with the corresponding f functions that are greater than 0, essentially that's going to optimize the problem. So that just to illustrate how this is different. So if theta was at a different location, let's say theta 3, then here, yeah, because the lines are intersecting and they have different slopes. So here now, if you could only recommend 2 items, then it is this green curve, which is for product 3. So you can only, so you would recommend product 3, and then the red line is the next highest one. So, and then you recommend product 1. Okay, and so yeah, so yeah, so just to simplify things, the optimal solution really comes down to finding this unique theta. You can use a bisection search algorithm for finding theta, or we discovered after implementing this, we discovered that, oh, actually, maybe if you're able to you know, have these lines, the f functions, they are fairly easy to calculate, then maybe you don't need to really converge on the theta. You just need to know the intersection point. So whenever the lines cross each other, then you just need to know. So once you know roughly which region the optimal theta falls in, then all you need to know is the rank of the f functions here, because within each region or within each segment, the ordering of the f functions don't change. And so that's what we call the sorting algorithm for this particular problem. Okay, so yeah, so this is a little bit more involved because you do need to find the segments first. However, once you find the segments, which may or may not be faster than really doing bisection search for the optimal theta, but anyway, once you find the segments, then you have a sorting algorithm. Okay, so we have 2 different ways to tackle the problem using the insights that we got from some analysis. Okay, so now, this is for finding the optimal substitution sets for the expected revenue maximization problem. Now, for the other types of problems, and especially for co-purchases, we discovered that actually the problem is not as difficult as for what I just described. So for co-purchases, most of our problems were actually solvable just by a pure sorting algorithm right from the start. So for instance, for the pure expected revenue maximization problem, you just rank the expected revenue of the co-purchase items based on the utility model. So this is definitely easier to solve. So we can use it for co-purchases for the pure revenue maximization problem. Similar results apply for the pure consumer surplus, expected consumer surplus maximization problem, and it applies for both substitutes and co-purchases. And this comes purely from the way the consumer surplus functions look like. And then it also works for co-purchases for the weighted average of revenue, expected revenue, and expected consumer surplus maximization. So this also applies to that problem as well. Okay, and finally, perhaps the most complicated and interesting optimization model is the one where we have pure revenue maximization, but with a variety constraint. So for this problem, we had to really look at the Lagrangian dual. So we look at the Lagrangian dual, and what we found is that, okay, so again, so for the substitution problem, so the problem decouples for substitutes and co-purchases. And the substitution problem is essentially the same as the expected revenue maximization problem. So we can use that bisection search or the augmented sorting algorithm. But for the co-purchase optimization part here, we can't do that because it is tied to the variety constraint. However, we found that actually the structure of this problem is essentially the same as before in the pure revenue optimization problem for the co-purchase optimization, except with this dual variable gamma. So so the problem for expected revenue maximization for co-purchase is the same as here, just without the gamma. So what this leads to is that maybe we can start with gamma equals 0. So again, gamma is the coefficient on your variety constraint. And so as you increase gamma, you're going to give more and more weight to the variety constraint. And so you're going to give more weight to the variety constraint. And so so what that means is that if you didn't have a feasible problem before, so that satisfy that variety constraint at gamma equals 0, then you just slowly increase the gamma until you do satisfy the variety constraint, and then we can show then yes, once you converge, that is indeed the optimal solution to the co-purchase optimization problem as well. Okay, and so because we have to do this iteratively, we call this essentially the augmented Lagrangian method. Okay, so we wanted to validate our algorithms and just to make sure we get sensible results on real data sets. Our industry partners, they actually directed us to this particular data set, which, by the way, it is available online for free, widely available. You just download it. So you can get it from both Kaggle, the data competition website. You can get it from Kaggle, but you can also just look it up on dunnhumby, which is like a data science company for retail analytics. dunnhumby also hosts this particular data set on their own website as well. So we're looking at what's known as the complete journey data set. And this contains household level transactions over 2 years from a group of 2,500 households. And we have observations of all their purchases and not just from some limited number of categories. We have everything. And for certain households, there is actually quite a bit of demographic information as well. Excuse me. Okay. Okay, so we considered 12 different examples with different levels of initial choice, so like different products to start with. So that's better. So here Q, remember, is the consideration set for substitutes, and R is for co-purchases. Excuse me. And K, remember, is the K, remember, is the size of the recommendation. I'm sorry. Let me just stop for a sec.
Yeah, just take your time. Yeah.
Okay, so let me say share screen. Okay, so I think that's gone now. So okay, so yeah, so Q, remember, is the size of the recommendation, the consideration set for substitutes. R is the consideration set for co-purchases. K is the the size of the recommendation. And so, of course, if your consideration sets are large, then you have lots of different combinations to be able to recommend. So yeah, so the computational time will be an issue as the consideration set increases. So we wanted to make sure we look at different sizes of the consideration sets. And we also wanted to just see how the results pan out for different types of products, and also different choices as well. Okay, so yeah, just mentioned that 5 are from the data set, and examples 6 to 12, they are kind of semi-simulated data, in the sense that we are using the data we fit a personalized utility model using the data set that we have, but because we it's not so clear, no, because we wanted to really control for the size of the consideration sets. So what we did is we simulated products that could belong to the consideration sets to generate these examples. Okay. All right. So okay. So yeah. So okay. So I have a bunch of tables to show you. I just realized, yeah, we don't have too much more time now. So yeah, so it's not that great looking at tables. So I'll just mention that, yeah. So we looked at, so as I've shown you in the summary of algorithms before. So we have like different types of problems, right? So we have problems for substitutions, problems for co-purchases. We have problems for expected revenue, expected consumer surplus, weighted average of expected revenue and consumer surplus, and also the variety constraint problems. And so basically, what we wanted to make sure is that the algorithms do find the optimal solution. So we're making a comparison against the brute force search, because of course we are able to do that for finite sets here. So we wanted to do comparison of the actual revenues as well as the computational times, because a very big constraint for the retailer to be able to actually use these algorithms is to be able to calculate this in real time, right? So computational time was absolutely of an essence here. And so yeah, so we wanted to, so here we did a backtesting case study using these Dunnhumby data sets to check that the algorithms do indeed optimize the whatever problem that it is supposed to optimize. So this is just looking at the objective values, and we find, yeah, they all do match. And then we also wanted to look at the computational times. So what we found is that when the consideration sets are fairly small, the brute force search is very fast because well there aren't that many choices or possible recommendation sets to look at. However, it's really when consideration sets become larger and larger, the clever algorithms, they do indeed beat out the brute force search. So for example, here, when consideration set is say 30, for this particular example here, we're looking at over 598 seconds for brute force search to find the optimal sets. But here it only takes about 4 seconds for the other two algorithms. And this is, of course, based on just a not so powerful laptop. Okay, and then yeah, so this is showing you the result for expected consumer set plus or recommended substitutes. We get similar stories here. Consumer set plus, recommended substitutes, calculation time, similar stories here as well. Expected revenue, blah. Yeah, so let me just skip to this one. Yeah, so let me show you this one. So for expected revenue with variety constraint. So actually, yeah, so this was very interesting. I think for this problem, so this is expected revenue maximization with a variety constraint. And here, adding the variety constraint really messes up the brute force search. Like, you really have to enumerate everything. And what we found here is, yeah, we do find many examples of our method being much faster, orders of magnitude faster than the brute force search method. And then, and I thought, yeah, I'll end it here. So here we can plot basically like a expected revenue frontier, where you plot the expected revenue on the y-axis and expected variety on the x-axis. And so again, because we're doing discrete optimization, so you see, so there is like certain types of recommendation sets will give you a particular revenue. But as you increase the variety threshold, so that constraint threshold is not going to satisfy that after a certain point, so it drops down here to a different set of recommended products, and then it drops down here to another set of recommended products. And this is just to show you that the iterated dual, the augmented Lagrangian method I described earlier, it gives you exactly the same solution as the brute force search method. Okay, so yeah, so that's my final slide, and I'll end it here for the sake of time. Okay, so I guess we have a couple minutes for questions.
Thank you very, very, very much for the nice presentation. As Gah-Yi has said, we have a couple of minutes to the audience, so if you would like to ask a question, please. Yeah, so Jasone, can we give the rights of the microphone and the camera?
Hello, are you able to hear me?
Yes.
Hello. Yeah.
Yes,
Hi, and thanks for the nice presentation. I have a question regarding the consideration set. Is it the case that your consideration set needs to be large, or even if they are small? Suppose I don't have a lot of history of the products. Like there are some new products, relatively new products, and there are some products for which I have a lot of data. So how do you deal with these issues in your paper?
What do you, okay, so I don't understand your question was, your question was, do the consideration sets necessarily need to be large? Is that your question?
Yeah.
Do they necessarily need to be? I mean, what you choose to be your consideration set, ultimately that comes down to the retailer's decision. It's like, you know, what do they want to do? So, okay, so here's the thing. So, okay, so what we did with the real data is the following. So we're like, as a customer, you're aware of certain numbers of products. So maybe there's some product that you always buy. So it's very clear that you know that particular product. But also when you think about a giant like grocery chain, they typically have lots of products that you may have never known about before. until you've been, you know, nudged to actually take a look at it. And so so what we have is that in our mind, the consideration sets would include products like that are new to the market, but also products that customer has never shopped before in their history. So that's how we consider to be good consideration sets. But ultimately, it is a subjective question, like what do you include in your consideration set? I mean, there is a bit of the science in that. Obviously, you can't include items the customer clearly knows about. But beyond that, you can make it, of course, as large or as small as you want. And I guess you're getting to the point of, well, if the consideration set is small enough, well, couldn't you just use a brute force search algorithm? Well, I guess our results show that, yeah, indeed, if the consideration set is small enough, and if you're in the right example, the parameter space, maybe it's fine to just use brute force search. But at the same time, in industry, now that I do some work for Amazon, I do have more of these insights now. In industry, you want as generalizable solutions as possible. So even if brute force search is pretty good for, say, small consideration sets, it could be that, you know, the next day you realize, or next month suddenly this brand introduces 20 new products within some category, and you want to consider all of them. So you don't want to be tied down by not using a smarter algorithm when you have it.
Thanks.
Thank you very much for the question. Are there other questions from the audience?
I can ask a follow-up question if there is not any.
Okay, sure. Yeah, your first question was a good one. Yeah.
Okay, so my first question is also related to this question is also related to the first one. So, I understand that if you have a lot of data in retail, these algorithms, do you think that if you have very small data, like a small data for each customer or a small data for each product, like a small data set, do you think the model that you presented would still be able to do good, or do you think you need to do something else?
If you don't have enough customer history,
yeah,
in the data, it would affect our model in the sense of not knowing the best consideration set for the customer.
Yeah.
Right, there will be errors. They will be basically fuzzy, right? Basically, small data means more error. However, but here's the thing: the beauty of using something like a personalized utility model is, and also if you're a big retailer, the beauty of that is you can draw upon customers who are similar to you. So even if you yourself may never shop from this particular shop before, once they sign you up onto be an online customer, ask you some basic demographic questions, then they can draw upon the history of customers similar to you and use that information to make a good guess for what your consideration set could be.
Okay, thanks.
Yeah,
Okay.
a very nice question. Thank you.
Thank you again, and thank you to you. We are going to close the session. As you know, we finish at 5:30. We are very thankful that you came today, even in the health circumstances that you have today. So we wish you a speedy recovery, and yeah, and thank you again for coming.
Thank you very much.
Yep.
Yeah.
And
Thank
see you next week.
Bye bye, everybody.
Thank you.